Today I'm going to talk about some work I've been doing at Manchester, funded by the Leverhulme Trust. It's work I've been doing with Steve Lind on implementing the log conformation formulation into smooth particle hydrodynamics, so that we've got a more robust solver for viscoelastic flows. This work is currently working its way through the review process, but if you want more information, you can find it on this archive preprint that's at the bottom of the screen. So a bit of background, what are viscoelastic fluids? They're fluids which have a short-term memory of their deformation. So in simple terms, they appear a little bit bouncy. Examples are things like shampoo, paint, whatever this gunk is in this container, bread dough or something like that. But they're very important actually. So they're found in a number of manufacturing, processing industries, relevant for the hydrocarbon industry, biomedical applications, and geophysical flows. And they're also really quite interesting. So I've just got some illustrations of some of the effects that you get. So they behave very differently to Newtonian fluids. So if you spin a rod in a Newtonian fluid, you get a sort of trough around the vortex, whereas in a viscoelastic fluid, the fluid climbs the rod. You have things like the K effect, where a jet of shampoo can bounce, and the Barris effect, where you extrude some viscoelastic liquid and it expands as it leaves the nozzle. And there's also phenomenon like elastic turbulence, which is chaotic behavior even at asymptotically zero Reynolds numbers. And they can be used to reduce drag, reduce turbulence drag. So they're really quite interesting and really quite important. But as I'll get onto in a bit, they present some fairly unique numerical modeling challenges. Previous viscoelastic SPH has been generally weakly compressible, and it's relied on artificial dissipation or stress or viscosity, so sort of tricks to make it stable. And it's been limited to really quite low levels of elasticity. Now there's methods that can get over these things, which have been used in other schemes like finite difference, finite volume, finite elements, but they've not been put into SPH yet, so it's really lagging behind other methods. So the equations that we solve, they are, initially we've got the conservation of mass and conservation of momentum for the incompressible Navier-Stokes equations. This US is a shifting velocity, so this is to account for the particle shifting technique based on Steve Lind's work. But you'll notice the difference in the momentum equation is we've got this divergence of the polymeric stress term. So this is the forces due to the molecular deformation of the fluid. Now, alongside these equations, we have to evolve an equation for the conformation tensor of the fluid. So the conformation tensor is a macroscopic measure of the microscopic deformation or molecular deformation of the fluid. So if we imagine that the viscoelastic fluid is a suspension of some Newtonian liquid with a load of long stretchy molecules represented by springs and dumbbells, this equation for the conformation tensor models the evolution of the average deformation of these springs. This term here is it's just a derivative that follows the motion of the fluid alongside its stretching and rotating. And then these two terms, the relaxation function and the strain function, they come from constitutive models which effectively describe the nonlinearity in the springs and the type of viscoelastic fluid that we're considering. So the key dimensionless parameters with our viscoelastic flows are the Weissenberg number, which is the ratio of elastic to viscous forces, and the Deborah number, which is the ratio of observation timescales, so elastic to observation timescales. And in certain situations, they are equivalent. But all we really need to know here is that a higher Weissenberg or Deborah number means that elastic effects are more important or apparent. So the numerical challenge, for a long time, people were trying to model viscoelastic flows, and they came across something that was called the high Weissenberg number problem, which basically limited the maximum Weissenberg number they could simulate to about 1. And above that, we started getting all sorts of instabilities, and codes typically blew up and crashed. Eventually, Fatal and Kupferman worked out one of the causes of this, which was that the velocity gradients in the conformation tensor evolution equation, they act multiplicatively. So we have these exponential profiles in the conformation tensor, which means we have exponential profiles in the polymeric stress. And finite difference, finite volume, SPH, all these polynomial-based numerical methods, they can't capture exponential profiles. So we were underestimating gradients and then overestimating the growth of stresses and leading to a blow up. So the solution, which they came up with, was to recast this equation in terms of the logarithm or the matrix logarithm of the conformation tensor. So they take the decompose the conformation tensor into eigenvectors and eigenvalues, take the matrix logarithm, and then when you reformulate this equation for the conformation tensor in terms of its logarithm, we find that the extensional component of the velocity gradient, that's B, acts additively, and effectively we've linearized the exponential gradients. So it's much more amenable to numerical discretization to solve the equations in this form. It has the added benefit that it ensures that the conformation tensor remains symmetric positive definite, which means that we can ensure that the numerical results we get correspond to physically meaningful molecular deformations. So this has been applied to most other numerical methods, but so far it's not been applied to SPH. So that's where we come in. So we've implemented this method in what I would say is a fairly standard incompressible SPH code. So first order projection method with Fickian shifting, second order mirror boundary conditions, and we've included an improved free stress, free surface boundary condition for the stress for low Reynolds number flows. We use first order correction for gradients. We have a color function, so we can handle multi-phase flows if we want. We also introduced something called elastoviscous stress splitting, which effectively takes some of the dissipation from the polymeric stress and shifts it across to the Newtonian component. And without changing the continuum equations we're solving, it effectively just allows us to stabilize the method a bit. So we've done a lot more validation than just this, and if you want to see more, you can see it on the archive preprint, but this is sort of the key result. So this is looking at viscoelastic Poisson flow, so flow through a channel driven by a pressure gradient. And for the Newtonian case, so that's this black line, it starts at 0 velocity and accelerates to a steady velocity with no overshoot. As we increase the elasticity, so we increase the Weissenberg number, we get overshoot and it bounces and rebounds. And the higher the Weissenberg number, the bigger the overshoot and the longer the time to reach the steady velocity. So previous viscoelastic SPH could barely handle this Weissenberg number equals 1 line. Here we've got red lines are our SPH simulation and black lines are the analytic solution. So you can see for our new model, we've got all the way up to Weissenberg number 1, 2, 4, 8, 16 being really very accurate. Above Weissenberg number of 16, so for 34 and 32 and 64, the accuracy deteriorates a bit, but we don't actually get a catastrophic instability. So this really represents quite a step change in the capabilities for SPH simulating viscoelastic flows. I'll just run through a few other validations and test problems we've looked at. So this is a viscoelastic drop landing on a solid plate. And so the color corresponds to the trace of the conformation tensor. So brighter corresponds to more molecular deformation. So we see for the Newtonian case, the drop just lands and then spreads out, whereas for the viscoelastic cases, it spreads out and then contracts and then spreads out a bit more. So if we look at the non-dimensional width of the drop, we see that it expands and then contracts and then expands, whereas the Newtonian case just expands and keeps on steadily expanding. So we compare this to existing finite difference and SPH simulations, and again we get pretty good results compared to previous numerical modeling. The next problem is flow past an array of cylinders, which is interesting because it's relevant for elastic turbulence, although we've not looked at that yet. So we've got a periodic flow in the x direction, walls at the top and bottom, and we can see the asymmetric form of the vorticity field and the molecular deformation. And again, we get a good match with previously published simulations. Finally, one of the key things we've looked at is viscoelastic jets. So when you have a low Reynolds number jet, it can buckle, and viscoelasticity can promote that buckling behavior. So with this model, we've been able to look at well, the effects of varying the Weissenberg number, the Reynolds number, and various different viscoelastic nonlinearity parameters, so for the different models, on the behavior of the jets and on the way they buckle. So for instance, we see that for just slightly different closure approximations in a constitutive model, we get a jet that buckles in a different direction initially. And again, these results, although it's difficult to compare them with experimental data because it's inherently a 3D problem, we get a good qualitative match with changes in buckling frequency. So just to conclude, we've implemented two new techniques, or they're new to SPH, the log conformation formulation and an elastoviscous stress splitting scheme. And these give us a much more robust viscoelastic SPH model. We've got new free surface boundary conditions, and the code works for multi-phase flow. So this is just an example of an instability, Kelvin-Helmholtz instability for different Weissenberg numbers. And I think the key thing is that with this formulation, we don't require any artificial viscosity or any sort of numerical tricks to stabilize the method. So in future, we're looking to look a bit more at multi-phase flows, maybe include surface tension, and then investigate elastic instabilities to see if we can reach higher Weissenberg numbers. So I think I've got a very brief amount of time for questions, so I'll end there.